My name is Sudipta Rath, and this is my constant velocity lab report. So the main goal of this lab is to compare an experimental model of an object moving at a constant velocity to a computational model based on Newton's second law. This lab allows us to demonstrate how Newton's second laws can predict the motion of an object in front of us. So all these formulas below that we will use in this lab are derived from Newton's second law. In the velocity update equation, we assume the net force to be zero because the object is moving at a constant velocity, which simplifies this equation down to the final velocity equaling the initial velocity. For the average velocity equation, we assume a constant velocity throughout, which means the average velocity is equal to the initial, which is equal to the final. So here's my experimental data, which I gathered using the Tracker app. I rolled a water bottle of uniform shape across a flat surface at a constant velocity. On the right, you can see my data points gathered at each time interval. The initial position of the water bottle is marked as the origin, so its motion is in the negative direction. The points are plotted to make a graph with time in seconds on the x-axis and position in meters on the y-axis. And we see that the graph is relatively linear with a negative slope. This is predicted of an object with a constant velocity because the slope of a position time graph is velocity. I used the experimental data to make a computer model using a program called GlowScript. I utilized the velocity update equation under the assumption that the net force is constant, which means that final velocity equals initial velocity, which equals the average velocity. I plugged in the initial velocity and the velocity at any given point of the object's motion. In this case, I used t equals 0.5 seconds in order to calculate the average velocity of negative 0.832 meters per second. In the GlowScript code, I edited the velocity to be negative 0.832 meters per second and ran the while loop for when time is less than 3.47 seconds, which is how long the bottle rolls for. I made the time step to be 0.033 seconds to match the time interval for the experimental model. So these are the computational models resulting from the GlowScript code. The position time graph is perfectly linear with a constant slope of negative 0.832 meters per second, which is the average velocity calculated. The velocity time graph is a horizontal line at v equals negative 0.832 meters per second as expected. So I ran both the experimental and theoretical data through Excel in order to generate a plot with both graphs. We have position on the y-axis and time on the x-axis. In red is the theoretical model and in blue is the experimental model. The steeper the position time graph, the higher the value of velocity. Up until about 1 second of motion, the experimental model lines up with the theoretical model. However, after that, we start to see some discrepancy as the experimental graph becomes flatter, indicating a lower velocity. So there are numerous possible sources for this discrepancy. Friction on the surface can slow the bottle down, resulting in a lower velocity as time progresses. Bumps and slant on the surface can impede the bottle from moving smoothly and uniformly, also resulting in a lower observed velocity. Additionally, human error in identifying the point of mass on the tracker at each frame due to blurriness can also cause discrepancy in the data. So how can we reduce error? In order to reduce error, we can ensure that the surface is completely flat and frictionless to result in a constant velocity. A camera with a higher frame rate can be used so that the point of mass can be easily identified at each frame. So what if the axes were flipped? The direction of motion would be considered positive now. So the slope of the graph would be positive rather than negative. The magnitude of velocity would remain the same, but the sign would change, indicating positive direction movement. So what does this mean? Theoretically, there are four main forces acting on the object as it is in motion. Once the object is in motion, the forces should cancel out each other out to maintain a constant velocity. So the upwards normal force cancels the downward gravitational force, and the frictional force cancels the applied force. However, we see that the object is unable to maintain the constant velocity due to the frictional force, resulting in a net force in the x direction.